Good morning, everyone. Today our topic is UV visible spectroscopy. So UV visible spectroscopy is having the range 150 nm to 800 nm. So it is divided into three parts: far UV region, near UV region, and UV visible region. Near UV region ranges from 200 nm to 380 nm. Far UV region ranges below 200 nm, whereas visible region ranges from 380 nm to 780 nm. So in near UV region, unsaturated compounds will be absorbed. In far UV region, saturated compounds will be absorbed. In case of visible region, colored compounds will be absorbed. When electromagnetic radiation strikes an atom or a molecule, it either absorbs or emission will take place. Absorption will take place, either emission will take place. If absorption takes place, electronic transitions are possible. If emission is taking place, emission spectroscopy will study under it as an emission spectroscopy. But UV visible spectroscopy comes under the absorption spectroscopy. By the addition of UV visible radiation on the sample will absorb the radiation, thereby it leads to the electronic transitions. See here the electronic transitions, lower energy level to higher energy level, that means excited state, ground state to excited state, the electronic transitions will takes place in general by the absorption of UV visible radiation. In between the electronic levels, there will be vibrational energy levels exist. In between the vibrational energy levels, electronic rotational energy levels will also exist. By the absorption of UV radiation, electronic transitions will be taking place. That means both vibrational and rotational transitions will also take place in the molecule. Coming to the principle involved in the UV visible spectroscopy, otherwise electronic spectroscopy, the principle is Beer-Lambert's law. Here, in order to explain the Beer-Lambert's law, we are taking a sample solution in a beaker and one source of light. So one monochromatic beam of light is falling on the sample, and whatever the light is falling, that light is intensity is I naught, intensity of incident light I naught, and whatever the light coming out, that intensity is known as a transmitted light intensity. So here, by the falling of incident light, some of the radiation will be absorbed by the sample, thereby the transmitted light radiation intensity will be decreasing. That will be detected by the detector, and it will be giving in the form of a graph. So absorbance is directly proportional to the concentration of solution, where A is equal to absorbance, that is equal to epsilon Cl is equal to log I naught by I. Here the terms are C means concentration in terms of moles per liter, where L is the length of light path through the cell, epsilon is the molar absorption coefficient, whereas I is the intensity of incident light, where I is the intensity, I naught is the intensity of incident light, where I is the intensity of transmitted light. Here, in case of UV visible spectroscopy, electronic transitions are possible. What kind of electronic transitions are possible here in UV visible spectroscopy? These four electronic transitions only possible, that is sigma to sigma star, pi to pi star, n to sigma star, n to pi star. Okay, here the sigma star, pi star, n, all these are, whereas sigma is bonding, pi is also bonding, whereas n is non-bonding, whereas pi star is anti-bonding, sigma star is anti-bonding. Okay, sigma and pi star, sigma is related to the saturated compounds, whereas pi and pi star are related to the unsaturated compounds. Depending upon the type of the transition, where it will be absorbing, and examples for the transitions. Here, sigma to sigma star transition, if we take, that will be absorbing in the region UV. An electron in bonding sigma orbital of a molecule is excited to the corresponding anti-bonding orbital by absorption of electromagnetic radiation. Absorption of electromagnetic radiation will take place. Sigma to sigma star transition requires large energy. Here the examples are alkanes and cycloalkanes. Alkanes and cycloalkanes, you can take it as an example. Here saturated compounds should be present. What are the compound you are taking it as an example? That should be a saturated compound. Next, coming to the second type of transition, that is N to sigma star transition. An electron excitation takes place from a non-bonding orbital to an anti-bonding sigma orbital. This is a symmetry forbidden and low intensity transition. This is found in saturated compounds containing a heteroatom with unsaturated pair of electrons. Here the example we can take it as saturated halides, alcohols, amines. Example CH3OH, anything you can take. Next comes another transition, third one, pi to pi star transition. An electron from pi bonding orbital is promoted to anti-bonding pi star orbital. This is a symmetry allowed and high intensity transition. This is found in compounds containing double, triple bonds and aromatic rings. For example, here alkenes and alkynes, you can take it as an example. CH2 double bond CH2, otherwise CH triple bond CH. Next comes the lost transition, N2 pi star transition. An electron from non-bonding orbital is promoted to anti-bonding pi star orbital. This is found in unsaturated compounds containing a heteroatom with unpaired of electrons. This is a symmetry forbidden and low intensity transition. Here the examples you can take acetaldehyde, or otherwise you can take aldehydes, ketones also. Next comes some of the important useful terms generally we use in the UV spectroscopy, that is chromophore and oxochrome. Chromophore is the part of a molecule responsible for the color in any compound. These can be any functional group with large number of pi electrons, like conjugated double bonds. Here you can take the example as C double bond C, C double bond O. Next comes another definition, oxochrome. Group which enhances the absorption of chromophore is called oxochrome. A saturated group containing non-bonded electrons and attached to a chromophore alters the wavelength and intensity of absorption. Here in this example, OH is known as a oxochrome, whereas C double bond O, it is unsaturated, is known as a chromophore. Next comes another definitions, just like types of shifts. Here the types of shifts, in order to discuss about the types of shifts, we will take a graph between lambda maximum on the x-axis and epsilon maximum, that is molar absorptivity coefficient on the y-axis. You will get a peak. Depending upon that peak, we will explain bathochromic shift, hypsochromic shift, hyperchromic shift, and hypochromic shift. We will see in detail. First one is a bathochromic shift. Bathochromic shift can also be known as a red shift. Shift of absorption maximum to longer wavelength in the spectra called bathochromic shift. Here the reason is the presence of chromophores and oxochromes, effect of solvent, and increasing conjugation. Here you can take example CH2 double bond CH2. Its lambda maximum value is 175 nm, and CH2 double bond CH2 CH3, that is 1 butene. Its lambda maximum value is 185 nm. Next comes another shift, that is hypsochromic shift. Hypsochromic shift, shift of absorption maximum to shorter wavelength in the spectra called as hypsochromic shift, or otherwise it is also known as a blue shift. The reason for the shift is removal of chromophore, oxochrome in the solvent and also the solvent effect. Here we can take the two examples, acetone, and another one is also acetone. It is involving in the hydrogen bonding. If it is removed that bonding, then its lambda maximum value will also decreases. This is the solvent effect. Next comes the third definition, hyperchromic shift. Increased intensity of absorption maximum is called hyperchromic shift. Lambda maximum will be large. Here you can take any other examples. Pyridine and pyridine is having the substituent CH3. That two examples we can take as a pyridine. Next, hypochromic shift. In case of hypochromic shift, decrease in the intensity of absorption maximum is known as hypochromic shift. Here we can take the biphenyl as an example. In case of biphenyl, CH3 group will be attacked. Thereby, the lambda maximum value will be decreasing. Epsilon value will decrease. Next, applications of UV visible spectroscopy, electronic spectroscopy. First one is detection of functional group, identification of unknown compound, structural elucidation of organic compounds, qualitative analysis, extension of conjugation, detection of functional group, detection of concentration of substances, examination of polynuclear hydrocarbons, etc. Thank you, everyone.